Welcome to TennaTalk, a journey of discovery about all things antenna. TennaTalk is a production of the Antenna Whisperer. That's me, Rudy Wiedemann, K7RAW, and it is generously supported and sponsored by the Las Vegas Radio Amateur Club. This will be podcast number 1 of a series of podcasts. This one is entitled Making Waves. It's where we start. So, we'll start by deriving Schrödinger's wave equation and move on to deriving Maxwell's equations for electromagnetism. No, not really. Didn't want to scare you there, folks. But in reality, we're going to cover some numbers to give you some context, and we'll also give you some useful formulas for relationships and starting points, and hopefully give you a deeper intuitive feel for what's going on. And then some tips and tricks to get you going faster towards success. So, some of the things we're going to touch on in this episode are how antennas work, why antennas might not work, transmit and receive antenna distinctions, useful references, myths and truths, system metrics, and general guidelines. So, let's get right into it. How antennas work. Let's look at the sequence. The transmitter generates a modulated voltage waves out onto a wire. The impedance between voltage and current converts that voltage into current waves. Current waves generate radio waves leaving the antenna. That's very important that it's the current, not the voltage, that generates the radio waves. The radio waves are launched either directly point to point or via skip off the ionosphere. The antenna converts the radio waves back into current waves at the receiving end. Current waves induce voltages back through impedance formula, and then voltage waves are detected and demodulated by the receiver. Now, let's look at some radio wave behaviors. Rules of behavior are very similar to optics in terms of absorption, reflection, refraction, and dispersion. So if you think about how things look when you reflect and scatter light off of things, then you'll begin to understand how radio waves operate. It's fairly similar. In addition, efficiency and balance. While on the one hand, transmitters are based on the output where the max current is located, receivers operate based on how much of the electromagnetic wave is captured and not where the current is located. That's a very important distinction. So a few key factors to keep in mind are transmit power, antenna radiating efficiency, gain and directionality in 3 dimensions, polarization of the electric field. Remember, polarization is always the E field, not the magnetic or B field. Propagation conditions, receive antenna aperture, and receiver sensitivity and selectivity. That makes the complete trip and makes it all come together. So let's talk a little bit about standing. A standing wave can be illustrated by a bathtub. Notice that the waves slosh back and forth, and as they hit the end wall, the wave tends to slosh upward high. As they move through the center of the bathtub, they're moving at the fastest speed. That's the current. And the height of the waves at the end are kind of representative of the voltage that is on your standing wave on your antenna. So certainly for a resonant tuned antenna on the transmit or receive side, this is the ideal case. That's a good way to look at it. Now let's take a look at the classic dipole antenna. We start with an open feed line. The feed line comes from the transmitter side to the antenna side, but we're not hooked up to anything yet. We'd like to feed current on this wire this way, on this wire going back this way in an even balanced sense, and the currents cancel. Once we bend open the ends into a dipole and unfold it, now we can radiate that out, and that current goes out to the negative here and comes back depleting electrons on this side, and we've sloshed electrons in this direction, and the currents add up. In free space, the impedance, the voltage over the current at any snapshot in time, is about 72 ohms. Here is a really interesting diagram of how waves operate on a dipole. The blue line indicates the current. Notice that the maximum current is in the middle, at the feed point in this case. The overall length is half a wavelength, which is classical for a center-fed dipole. Now, when the electrons get to the end, they slosh high, as we saw before, and the voltage gets maximum positive here and maximum negative here, but on an absolute basis, it's maximum. Notice that the lowest impedance is at the center. That's because we have the highest current and the lowest voltage. Voltage over the current is impedance. Low voltage, high current, very low impedance. Relatively speaking, relative to thousands of ohms, we're down at 50 ohms. Hence our 50 ohm feed line matches to that. When the electromagnetic flux of the electrons going along the wire gives you a maximum voltage and a minimum current at the ends. That's the highest impedance. We could see a couple thousand volts and very low current. And so having impedances of several thousand ohms is not unusual here. Somewhere in between is a trade-off between the voltage and the current and the resulting impedance, somewhere between 50 ohms and thousands of ohms of impedance. And this is very important to look at. Now, how does a changing length in the dipole affect the magnetic waves, or I should say the electric waves that are trying to be propagated by the antenna? Well, ideally, if you're at halfway full length of the dipole from end to end, you're going to get a nice current curve. Again, these are the current curves because that's what generated electromagnetic waves. As you move towards a full wavelength, notice we get two half wavelength lobes. Well, guess what? The impedance here gets to be really high because it's a low current and a high voltage. And then as we stretch it out to 5/4 and finally 3/2, once it's 3/2, I've got three waves, okay, of current going here. And at this point, I've kind of gotten back to a reasonable current and reasonable voltages, which is back to somewhere around 50 ohms. And this relates to, you may have heard that a antenna that'll operate on 40 meters when operating on 15 meters, fed at the same center point by 50 ohm coax, will also work, okay, because you've got three lobes, which means 3 times the frequency. So there's a little trick for you. Now, on vertical antennas, we have our dipole, and let's turn our dipole on its side. And with the dipole on its side, this becomes our vertical radiating element. This becomes our ground or counterpoise or radial system. And how it works is that the vertical portion of it radiates out and the grounded portion creates a mirror type reflection. And we're actually creating an image of this vertical radiator into the ground, into the earth. And guess what? That radiates out as well, at least from an electromagnetic point of view. It seems to radiate out just like it would radiate out from a dipole oriented in a vertical direction. What you're doing with a vertical is you're trying to create an ideal dipole, but with only half the height of a half the dipole as your vertical radiator. So that's how verticals work. Notice that the ground needs something, needs to provide something that the vertical radiator needs to operate against. Here I've got a springboard diving board. Notice that the springs have some springiness at a certain distance with a certain springiness, and the board itself, of course, has some flex. That gives it a certain amount of tuning. If you had a diving board that was very, very stiff, and you had a very small child on here, it might as well be a piece of concrete. If you had a very heavy person and the springboard was very flexible and the springs were very light, then this thing would flap all over the place and would not be a very good springboard to jump against. Somewhere in the middle, depending on the height or the weight of the person jumping on it, is the loading of that springboard, and hence the loading onto your counterpoise or ground or radials. That's very important, that the radiating element actually needs something to work against, and that's the whole concept of grounds. We'll get into this more in future podcasts. Now, I want to spend a few minutes on this. This looks very complicated, but it kind of goes back to that antenna length thing I talked about, 40 meters versus 15 meters. What I've got plotted here are current curves across a dipole antenna. This here is the half wave curve, and let's just think of this as a 40-meter antenna, okay? And so that's about 20 meters from end to end. All right, quarter wave is 10 meters. Notice again that the middle is 50 ohms, and that's where we would normally feed it. However, if we want to operate on other bands, we could operate that same antenna fed at the center with a 50 ohm impedance on 15 meters. Where is that curve? Well, guess what? It's the green curve. So follow the green curve. I have one node lobe, another lobe, and I have a third lobe that makes three nice lobes that fit within the same 40-meter half wave antenna dipole. However, what happens on 20 and 10, etc., 12 meters, 17 meters? Well, let's take a look at 20 meters. 20 meters is the brown curve. I've got two waves. Well, that you'd say might work, except I've got very, very low current and very high voltage. So I've got very high impedance, okay? And you say, well, what about 10 meters? Well, that's the purple curve. I got 1, 2, 3, 4 waves, okay, of current on here. And again, the current is very low, and therefore the voltage very high. It's not going to be 50 ohms, it's going to be very high impedance, and I would need to have to match to that deliberately. So how do I get a 50 ohm coax to talk to and load up and operate all these bands at the same time? Is that possible? Yes, it is possible. And two ways to do it. One way is to use a off-center fed dipole. Let's say we feed it at this point. Well, for the half wave, it's kind of okay, but the matchup gets better and better and better to the peak, the closer, the higher the frequency we get. And that turns out to be somewhere on the order of 450 ohms. I've plotted here on this light blue line kind of a quality factor or goodness of maximal current, okay, across all of a combination amalgamation of all of these waves, and that's what this light blue curve is, okay? And this light blue curve actually peaks out here at 450 ohms for an off-center fed dipole. Now, will that match to 50 ohms? No, you'll need something to match it up, and we'll get into that when we get into the getting efficient podcast. Now, the other antenna that we can use is an end-fed half wave. Well, guess what? This is a half-wave antenna, a crosshair, but we're going to feed it at the end. Now, what's happening here? All these current curves are converging here at the end, all coming down to a low current and therefore a very high voltage because the power is the same. You end up with somewhere around 2450 ohms of impedance at the end, and you have to now match it very differently to your 50 ohm coax when you do that. But when you do, you can operate across all of these bands within the 20-meter long dipole for the 40-meter band. If you want to operate 80 or 120 meters, however, you're going to have to stretch that line even further to be a half wave on 80 meters or a half wave on 160 meters, and then more of these different waves of the different bands will fit within it somewhere. So that's some of the concepts of the center fed, off center fed, and end fed half wave dipole. Now let's take a look at the classic antenna system. This side up here is the rig side of the antenna. This side up here is the antenna side of the antenna. We start with the rig in purple here. We might have an antenna tuner, and that's why it's dotted, it's optional. And we might have a current choke, that's a CC, and that's dotted and that's optional. We'll come back to that in a second. And we take that coax feed line and we run it from the shack up to the antenna. Now we put a current choke. Now notice it's not dotted anymore. It's pretty much required in most cases. There's a few exceptions, but in most cases it's required. We'll talk about why that is. That may or may not go into an antenna tuner that's remoted and located at the feed point of the antenna, which if you're going to do it, it's a great place to do it. You might also be using a balun or unbalun up here at the antenna. In the case of a dipole or a more or less balanced antenna, that'll go straight up to the antenna. In the case of a vertical, you might have a ground or a radial or a counterpoise that is that springboard for the antenna element to work against and bounce against and help your signal get out. Talking about the current choke, there's several current chokes, and we'll get into it in the future podcasts, but why would this be more mandatory at the antenna than at the shack end? Well, what this does is it isolates your entire antenna past that point on the antenna side of the feed line from becoming part of the antenna all the way back to the shack. So it basically is, think of it as an antenna isolator, and sometimes it's actually called an isolator. Sometimes it's called a one-to-one balun. And as we'll see later, don't get confused between current baluns, which is the current choke style, or a voltage balun, which is used to convert one impedance to another. So I want you to see and think about antennas as a system. Now, why might antennas not work? It might be a poor design, bad impedance match. It might be bad construction. You didn't do a good job building it or tuning it, or you've got bad solder joints. A number of reasons. Could be shielded by ground materials or structures nearby. Could be below the ground like blockages like buildings or mountains that the signal's hiding behind. Could be bad propagation conditions from solar-driven activities, bad solar day. Or it could be local sources of background or of noise like power lines. Now let's take a look at transmitting antennas. Transmitting antennas, you would like to have a uniform or as much as possible current distribution across the antenna. And remember, current is what creates electromagnetic waves. You'd like the highest current portions up high. Give you an example. In the center of a center-fed inverted V, the highest current is at the top or apex of that inverted V, And if you get that above other buildings and obstructions, you've probably got a pretty good signal going out. Thicker elements give you a better bandwidth and transmit power. For example, this is why often you see tubular aluminum being used for some antennas, especially beam antennas, than simple wires. Wires will work, but tubular gives you much more surface area. It's because RF operates and moves up and down the wires on the surface of the wires. And therefore, if you have more surface area, it makes it easier for those electrons to move. And it should be well impedance matched across the entire system. Again, we'll get into that in a future podcast. It should have efficient matching devices, things that are not lossy, things that don't have losses when they heat up, like baluns that are undersized, underspec'd, or lossy feed line. It should be cut to resonant lengths if possible, and the antenna should be able to see past obstacles within its launch angle range. So if you're aware of the launch angle of your antenna design, vertical or horizontal, and it will be able to get out and travel past it or see past it, then chances are you have a better performing antenna for transmitting. And your local noise sources are really not a factor. It doesn't care. It doesn't really affect the antenna. And as well, other antennas that are not operating in the vicinity also don't tend to interfere with transmitting electromagnetic waves. And then finally, you want a good ground. And we'll get into grounds and all about grounds, counterpoises, and radials in future podcasts. Now, on the receive antenna side, longer lengths of antenna capture more of the RF, and that's called aperture, a larger aperture. Basically, if you were looking at a light bulb through a slit in a piece of metal, and that slit is larger and larger, chances are you're going to see more light. It's also well exposed. It's up high in the clear to catch those incoming RF signals. It's away from local noise sources, RF interference and electromagnetic interference. RFI is interference through the air. EMI is interference through conductors, very often through your power supply from your wall outlet. Thin wires work fine for very low current. No grounding is required, and a separate receive antenna can be very, very helpful, especially if you're using it with an SDR pan adapter. If you do that, you want a TR switch to isolate your transmit power from your SDR input. Couple refreshers. I told you we had a few formulas, so don't get scared. Wavelength, which you'll see is the Greek lambda here, is defined as the speed of light divided by f, the frequency, the resonant frequency. So it's 300 million meters per second divided by 14 megahertz, which is, for example, 20 meters. That comes down to a wavelength of 20 meters. Voltage SWR is defined by the ohmic resistance RO plus the radiation resistance R sub R divided by the impedance. And so it can be plus or minus 1. And we'll see that voltage SWRs, or SWR for short, if you have a radiation resistance of 25 ohms with a 50 ohm feed line, or a radiation resistance of 100 ohms with a 50 ohm feed line, in both cases, you get an SWR of 2.0. Now, these are some of the typical half wave lengths of both dipole pieces, okay? Oh, no, I stand corrected. This is actually each element of a dipole. So each element of a 10-meter dipole is about 8.1 feet. Each element of a 20-meter dipole is 16.5 feet each side. A few figures of merit. You've heard about Q factor in all likelihood. Well, that's the center frequency divided by the bandwidth. So a high Q factor is very narrow. If you have a very narrow bandwidth, you have a high Q. Also, S units, as seen on your receiver, is about 6 dB, decibels. And 1 decibel is defined as 10 times the log, or the base 10 log, of the output power over the input power. And so 3 dB reduction is approximately half the power or double the power if it's a plus 3 dB. You might see dBm and you might see dBi. Well, dBm is related to 1 milliwatt of input power. dBi is compared to isotropic. In the case of a perfect tiny point source light bulb, it sends out the same amount of power in all directions of a sphere. That's isotropic. Okay, dBd as compared to a dipole. Then other thing I want to point out, just to put you into a kind of a right calibration frame, that if we compare taking 100 watts radio and amplifying it to 500 watts only yields a 7 dB gain, or just over 1 S unit improvement. However, we can get similar antenna improvements and efficiencies if we improve the antenna efficiency and directionality. But amplifiers will not improve your reception, but better antennas will generally improve your reception. So if you think about your bang for buck, I would always start with your antennas. Next thing is a little bit about logarithms. Don't get scared, it's pretty straightforward. The 10 log of a number is simply written as 10 with a down here, log 10 of the number. It's the exponent of 10 to get to that number. So 10 to the 0 is 1, therefore the 10 log of 1 is 0. So it's the inverse of the exponent. We can just follow this all the way down. 10 to the 3 is 1,000. The log of 1,000, that is the base 10 log of 1,000, is 3. There are other bases, base 2, base e, which is a natural logarithm, which you'll see as ln instead of log. And then 10 to the minus 6, 1 millionth. Well, the 10 log of 1 millionth is minus 6. Now, let's talk about the relationship of S units to volts and dBm and millivolts. So you'll see that you can go from an S9, 10 over S9, 160 microvolts. It gives you negative 63 dBm. And remember, that's relative to 1 microvolt. And that relates to the logarithms we talked about earlier. And you can do the math for yourself. So if you hear about dBm, or you hear about microvolts, you hear about S units, you now have a way of doing the conversion. We talk a lot about SWR. Everybody's trying to get a low SWR. And they sometimes get really carried away on getting upset about getting below 1.5 or 1.3. Well, let's really take a look at the losses here to kind of get real. An SWR of 1.5, which is pretty common, is only a 4% loss, or a negative 0.18 dB. An SWR of 2 is only an 11% loss. It's not the end of the world. You have to get to an SWR of 6, which most rigs will not handle, by the time you're down to losing half your power. And that's on the total antenna system in terms of SWR. So don't get too terribly wrapped around getting much below SWR of 1.5, because you see, it only drops off a couple percent in terms of reducing your losses. It's more important that you get on the air. It's more important that you get the antenna up as high as possible, some of the other factors we talked about. So now let's talk about a couple antenna myths. Number one, My favorite. An antenna tuner at the rig makes an efficient antenna. No, not so much. A rig tuner really makes the coax, the impedance of the incoming coax, look more favorable to the rig so that when it transmits, it's not trying to reflect a lot of that power back into the rig. It's adjusting the overall system to be a little bit more tolerable or swallowable by the transmitted power from the rig. A resonant 50 ohm dipole doesn't need a common mode choke. Wrong. If you do that, the braid or shield of your coax will be part of your antenna system. If you ground it, if you move it around, if you put it near metallic objects or other antennas, guess what? It's going to change the SWR all over the place, and it's going to be part of your antenna system. So use a common mode choke at the feed point and isolate that antenna from the coax. It also prevents getting any RF down that coax on the outside of the braid into your shack, causing sometimes known as mic bite, RF sting or bite on your rig or on your microphone when you pick it up. A proper ground or counterpoise eliminates RF in the shack. No, not so much. We talked about the common mode choke. That's what eliminates RF in the shack. A proper ground or counterpoise is good to help your antenna efficiency, but it doesn't really help that much to eliminate RF in the shack. Open window line or ladder line is better than coax? Not necessarily. Sometimes it can be, sometimes it might not be. Most of the time, a properly designed and built system with coax is about as good as window line and ladder line in most cases. There are some cases when you're doing things like a G5RV, which is a combination of coax and ladder line. That's a kind of a interesting odd duck in and of itself. Ladder line can be useful. Ladder line's typically 300 to 450 ohms, which is way higher than coax. Feed line length is critical. If you've got a properly designed and balanced system, it tends to be not so critical. People will talk about, oh, you have to have an odd quarter wave of feed line to operate. No, feed line is usually sold in standard lengths of 25, 50, 100 feet, etc. So don't get too shook about that. Very little of your losses are going to be in a good quality feed line like RG8X. You don't need a balun or a choke, any balun will do. No, again, we'll find out. We'll actually go through the actual design and calculations of exactly what kind of balun, and or choke you might need. Why? Any ground point as good as another? No. You should always have your rig grounded, well grounded in the shack, and of course you should use a good lightning arrestor outside, upstream of the rig. That is grounded to an excellent ground rod deep in the ground. But some antennas don't need grounding. Ideal dipoles don't need grounding. A good transmit antenna makes a good receive antenna. Well, if you've got an ideal resonant transmit antenna, like an ideal dipole set up properly, it can make a very good receive antenna for that band. And not so good in other bands because it's going to tune out and reject other bands to a great extent. So no, that's again is a myth. Now let's switch to antenna truths. Reciprocity only applies when using a resonant antenna. Reciprocity is the concept that an antenna in transmit mode will be as efficient in receive mode. If you've got a resonant antenna well set up, that's generally true. But sometimes that's not true. Sometimes we can transmit our signal out through our launch angle, out over the top of objects, and still have the antenna for the receive side be kind of shielded from, because those waves come in from all angles. And so there are asymmetries there to be aware of. We'll talk about that here in a minute. Current dominates transmitters, voltage dominates receivers. It's the voltage per meter that's captured by a receiver, and it's the current, as we said before, that dominates where our electromagnetic waves are mostly being generated on our antenna. A better antenna is often more effective than an amplifier. We've already seen that. Just because the SWR is 1.0 doesn't mean it radiates. Good example, a dummy load is an SWR of 1.0, and hopefully it doesn't radiate. It's designed not to. So that's a good indicator, but it's not sufficient to tell you that you've got a great antenna. Antennas need ground or counterpoise are unbalanced. Well, that's generally true. If you need a ground like a vertical, okay, on a car where the vehicle itself is a counterpoise or kind of a moving virtual ground, or a ground plane for a ground-mounted vertical or elevated radials, those antennas are unbalanced and your coax is unbalanced. And if the antenna itself is 50 ohms and your coax being 50 ohms, you've got a pretty good match up there. Good elevated radials can in fact be an effective counterpoise. As few as 2 radials as an elevated radial, but better yet more radials, makes a pretty darn good counterpoise, and some classic antennas have been designed with elevated radials. A tuned counterpoise can be very effective. I found this out very recently for people working totally portable, walking about or even bicycling around, that they drag a long counterpoise wire behind them that they tune separately from the vertical whip. And it can make a huge difference, which you can hear on the receive side. You can peak it out that way, and then you can peak it out by maximizing the current into the counterpoise separately from tuning the antenna vertical whip portion. And in fact, MFJ offers what's called an artificial ground with 2 separate sections, a tuner for the antenna radiator and a tuner for the counterpoise. And it can be very effective if you're operating verticals. Polarization becomes irrelevant after the first skip. So unless you're doing point-to-point, I wouldn't worry about polarization. And it's what's radiated in the right direction that counts at the end of the day. Feed line length is not critical when its impedances are matched, the load to the feed line. So we talked about that before. Let's look at a few metrics. The ideal antenna operates on many bands, has very high performance radiated per watt injected. It gives us a shape more in the direction we like over the non-interesting direction. It gives us a good launch angle, so we get lower angles for a longer skip. It gives us wide bandwidth without having to retune. It's affordable, it's reasonably sized, and it's not too complex to set up or take down, and it doesn't attract a lot of unwanted attention. So some general guidelines. Higher off the ground is better. It drops after half wavelength in terms of performance. Naturally resonant is better, usually especially for single band antenna. Naturally balanced antennas are better. Longer is better. Higher Q is more efficient, but as we saw before, narrower bandwidth. Bandwidth narrows logarithmically with lower frequencies. Thicker elements give us broader bandwidth. Fewer smaller matching components increases efficiency. A better RF emitter is usually a better RF receiver, but only in the ideal case. And using balance unends and common mode chokes appropriately can be very helpful. So, some of the upcoming podcasts you see here, we'll be covering a lot of very, very interesting, useful territory to give you lots of hands-on tools to understand what's going on, to clarify things that you might be fuzzy about, to reveal some things that you weren't even aware of that can be very useful and very powerful. And tools like the Nano VNA and the Smith chart will be very powerful tools for you indeed, and really will help you amp up your game enormously. So the caption on this says, yes, I really am running just 5 watts QRP, although I suppose I do have an above average antenna system. So I think that's an understatement. So I think we all can be jealous of this fella, but it's probably not very likely where you live. Anyhow, the next podcast will be about getting heard. So contact your local club about a Q&A Zoom session around this podcast. And again, if you like this, please subscribe. Please click the like button and the bell for notifications so that you can be aware of the next podcast in this series of TennaTalks. And hope you enjoyed it. And if you did, please leave comments in the comment section about what you learned, how it might have helped you, and what you might have done with the information. So until next time, this is Rudy, K7RIW, your antenna whisperer, having a great time with ham radio, and enjoy your day. Bye-bye.